This is Jun2006 A21. A body moves with simple harmonic motion in a straight line. During this motion, the force in the body is proportional to the displacement from the equilibrium position and is in the opposite direction to the displacement. So here you have an A proportional to minus x graph. You can see that A is proportional to minus x there. Explain how figure 4.1 shows the force in the body is proportional to the displacement of the body from the equilibrium position and that the force is in the opposite direction. So we can tell from the graph, straight line through the origin. That A is proportional to x. And the graph also has a negative gradient. Therefore, A is proportional to minus x. But from F equals ma, F is proportional to A. Therefore, F is proportional to minus x. So there's your 3 marks for getting all those. Part 2. Use figure 4.1 to find the amplitude and period of the motion. So we need to go back to the graph again and have a wee look. We can tell first of all that the amplitude of the motion is minus 5 or plus 5. So the amplitude of the motion is 5. So x naught, so that's your maximum displacement, is minus 5 or 5. And then we have to find the omega. So from the graph we know A is equal to minus omega squared x, and if we do y equals mx and it's a negative gradient, then the gradient of the graph is equal to omega squared. So we have to get the gradient of the graph, and therefore the gradient is equal to omega squared, and that's equal to 2 pi. Omega is 2 pi over t all squared. And so once we get the gradient, that's equal to 2 pi over t squared. So the first part was easy. This part's a little bit more awkward. And so the gradient of the graph, I'm just rearranging that. So t squared is equal to 4 pi squared. Don't forget to square the 2, divided by omega squared, which is the gradient of the graph. Okay, and that's equal to 4 pi squared, and the gradient of the graph I calculated from 7.5 divided by 5 there, and just watch, that's 5 by 10 to the minus 3, so just watch the units there. So it's 7.5 over 5 by 10 to the minus 3, and the answer comes out to be the square root. T is equal to the square root of 0.026 seconds squared. It comes out to be 0.162, and the amplitude, of course, was 5 millimeters. Now, there's an awkward question coming up. Write revision notes suitable for this exam on the subject of damping and resonance. The spec gives the guidance, descriptive treatment of frequency response, resonance and effective damping. Bullet points illustrated by sketches and or graphs will be sufficient. So the first thing probably is to draw your wee graph. And your wee graph has got amplitude and driving frequency on it. And amplitude. And so there's your graph there, and there's your natural frequency f naught. And so whenever you have a damped graph, again they're looking for the frequency being about the same. So I'm just going to draw it broadly and hope for the best there. So that's your damped graph there with the D on it. And so now you have to explain that. I'll give you 1 mark for your graph. So an oscillating, so we're going to talk about the oscillating system. Forced to undergo vibrations. The frequency is varied, and then the amplitude observed. Now that's guaranteeing you 2 marks there if you say both of those things there. And then you've got another mark to get, another 2 marks to get So they're looking for labels on your graph. So if you have labels in your graph to show the maximum frequency and the resonant frequency, the maximum amplitude, sorry, and the resonant frequency, and then another mark for showing that the damping effect gives you a broader frequency response and a smaller amplitude. Shh, and a smaller amplitude.